People argued online for years, threads, memes, and hot takes, but arguments don't beat receipts. The fastest way to end it is to stress test the story in the harshest place the moon offers. Mystery at the moon's deadliest place ends debate in one pass. Not a dozen little pieces, but one pass. Independent verification beats staged footage. Elon Musk likes that idea. Evidence that you can check beats acting. Elon Musk often says that independent verification beats any staged footage, and he's right. Today, that evidence lives where sunlight never reaches, where it is so cold that even gases freeze, and where modern cameras finally see what used to be pure black. First, let's define the deadliest place. Near the poles, the sun hugs the horizon. High ridges bask in long light, but the lows, deep craters, never see direct sun. Those are permanently shadowed regions, or PSRs. Think of them as islands in the dark. As of a few years ago, we had mapped hundreds of them. 324 known PSRs, mostly clustered around the poles. No sunshine, no warmth, no easy power, and almost no margin for error. If you were going to fake the moon, this is the last place you would pick. If we can see, measure, and model these places precisely, the physics that Apollo lived by gets tested at maximum difficulty. Shackleton Crater is the poster child. It sits at the lunar south pole about 13 miles across. The rim is bathed in near constant light because it sits high. But the interior? Perpetual night. The floor is so cold that anything volatile, water vapor, carbon-based gases, hits the ground and freezes. That makes Shackleton's interior a natural freezer. It also makes it unforgiving. According to the mapping work done over the last decade, mission teams now treat its illuminated rim as prime real estate for landers and power, while treating the shadowed interior as a scientific goldmine and an operational hazard. Both things can be true. Think of lab fingerprints that only real lunar material carries, plus visible receipts that you can check from orbit. Seeing into absolute darkness used to be impossible. Ordinary cameras rely on reflected sunlight. Inside Shackleton, there is none. That changed when a new ultra-sensitive camera started flying in lunar orbit and captured the clearest views yet of a permanently shadowed floor. One early image covered a slice about 2 kilometers wide inside Shackleton's darkness. You can make out surface texture and slopes that were invisible before. Pair that with the South Pole visualizations that track the sun grazing the horizon, and the geometry clicks. Long razor shadows, sudden brightness on the rims, and pools of black that stay black all month. High-resolution spacecraft in lunar orbit have image descent stages, equipment, and disturbed regolith at Apollo sites. There's another leap. We can enhance the limited light using deep learning, an algorithm trained to recover detail from near-black images. Feed it multiple low-light frames, and it teases out crisp features, boulders, ridges, and gentle slopes that a rover could actually drive. This is not hand-waving, it is repeatable processing that anyone can rerun with the same data. Put simply, we now have eyes that work where the sun doesn't. That turns trust me into see for yourself. One set of rules, many effects, all consistent. Now we hit the heart of it. 2 receipts from one place. On the visible side, the new imaging shows what's on the floor and how the walls shape the light. On the physics side, PSRs act like recorders. They are so cold that they trap water, ice, and other easy-to-evaporate materials. They also sit in a vacuum where the solar wind sprays the regolith with tiny particles. That implantation is the same space-weathering signature that we saw in returned samples. Solar wind implantation leaves a chemical trail in the grains. Different method, same physics. Imaging shows the terrain and the thermal shadowing. Cold trap chemistry and surface processes explain why it looks that way. When both lines agree, rumors lose oxygen. There's timing too. The moon didn't always have PSRs like this. As the moon slowly migrated away from Earth, its spin axis reoriented and settled into a stable configuration. After that change, these permanent shadows appeared and then grew. So many PSRs are younger than the craters that they sit in, but they've still been cold enough, long enough to archive the environment. And that is perfect for science. It means we can tie terrain that we see today to long-duration conditions that preserved water, ice, and other volatiles. Imaging tells you where to look, physics tells you why it stayed. Now zoom back to Shackleton's inside story. The interior walls have complex slopes, terraces, and texture. The floor is not featureless. It has subtle relief where frost might pool and where boulders cast deep, unmoving shadows. When you understand the shapes, the thermal behavior follows. Surfaces facing up to the sky radiate heat away, surfaces facing the faint scattered light glow a bit more. According to mission designers, those differences will guide rover routes and sampling. It isn't a guess, it matches the imagery and the environmental math. Now let's run the myth checklist from this polar vantage. Why no stars? The answer never changed. Exposure. Cameras set for bright foregrounds don't capture dim stars. At the poles, the sun's grazing light makes contrast even harsher. Rims are bright, shadows are black. Inside PSRs, cameras are specialized and tuned for faint light on nearby surfaces. They still won't pull stars unless they change settings dramatically. Look at modern polar images. You see surface detail or you see stars, not both at once. That's not a problem, that is how cameras work. Dust should billow. And air? Sure. On the moon, there is no air. Rocket exhaust kicks grains on ballistic arcs. They rise and fall. No clouds, no lingering smoke. Surface dust is ultra-fine and can charge under sunlight, hopping slowly in electric fields near the line between day and night. Near the poles with the sun low and shadows long, you get sharp edges and powder that behaves like powder in a vacuum. The crisp footprints and sharp shadows and the way that plumes clear and settle in seconds all line up with what we see in polar imaging and with basic physics. It is a place that we all can visit and measure. Radiation makes it impossible. Well, radiation is serious, not magical. The surface actually records radiation history in the soil. Mission planners account for dosage with time limits, shielding in vehicles, and choosing routes wisely. PSRs add a twist. They preserve volatile clues about the radiation and thermal environment because they stay so cold. None of this contradicts safety planning from decades ago. The playbook is measure the environment, limit exposure, use the terrain. The harshest place reinforces the logic, it doesn't break it. Here's the final nudge that kills fakery. Rivals. Multiple nations are converging on the South Pole. Shackleton's sunlit rim shows up on shortlist for human missions because it offers long light for power and line of sight for communication. At the same time, another major program is designing a mission to aim at PSRs with high-precision landings near the rims. According to public mission goals, they want to image, sniff, and sample exactly these forever dark pockets. That means independent teams will put cameras on the same ridges and dip sensors into the same cold floors. If one group lies, the next one exposes it instantly. The moon itself stores the proof in its soil. Competition creates the strongest argument for truth. You can't maintain a stage when the other guy is filming your set from 3 angles. South Pole mosaics are already public. Lighting models are public. The new ultra-sensitive images are public. The deep learning methods are published and repeatable. You don't need to trust a spokesperson. You can stack the evidence yourself. That is why the deadliest place is the perfect place. It supplies hostile environment receipts that anyone can check. And remember the human angle. The tech is catching up to the terrain. We now know which peaks see light most of the month and which valleys never do. We have maps of where a rover could tread without sliding, where wheels would bite, and where a drill might pull up frozen soil that has slept for eons. When the first crews build outposts near those rims and send robots down the shadows, the data stream will be relentless. Video, spectra, temperature curves, and samples. Each one a receipt. Each one another nail in the coffin for conspiracy culture.